This recording, okay, I'm sharing my screen. Did I tell you guys I recorded a health video just like a week ago? I spent probably an hour doing it, only to realize I hadn't been sharing my screen that whole time. It's the worst. Anyways, okay, so before we go there, I want to go to Moodle. Okay, so the grade breakdown is going to change slightly just because of the, well, what we're doing here. So, so I'll let you guys know what that is, and then what I'll do is I tried to update kind of the weeks, or at least for this week, what we're doing. My goal is, so for today, to finish 7.2 to 7.4, or 7.6, sorry. We'll see. I've got quite a few notes, and I really don't think that we'll get to the end of 7.6, but at least it's a good goal. And then we'll start chapter 8 next day. And then what we'll do is we'll just kind of keep going 8.4 to 8.6, and then finish chapter 8 next week. And then we've got 1 day for logistic regression. But I gather that you guys have used logistic regression already, so it might just be a nice review. And then we'll do the review for the final exam. So, which isn't really a final exam anymore. I'm calling it a final quiz. Oh yeah, so here I posted the figures for March 23rd. So if you grab those later or whatever, then that should be good. We also, where's the lab 5 here? I'll start putting these notes in my notes so I can give them to you later. Let's see here. Lab 5. Well, it's nice to have this thin pencil, but it's hard for me to write. So lab 5, I made it due Sunday, March 29th instead, at midnight, essentially, right? And so, because I think you guys needed more time, and honestly, if you need even more time, then just let me know, because we'll just kind of go easy from here on out. So we'll do lab 5, and then that'll be good. And I think I might have even bumped the assignment 8 due date. Yeah, assignment 8 is now due March 30th instead. So assignment 8, assignment number 8 is now due March 30th instead. Okay. At 11:59. Okay. So our new grade breakdown. New grade breakdown is going to be 50% assignments. Right, so you want to make sure that you're doing those quick little Moodle quizzes, because those are your assignments. And then for the labs, we're going to do 25%, mostly because I know you guys are spending a lot of time on those, and I feel like the grades have been pretty good, so I feel good about making those worth 25% of your grade. And then what I said was we'll just do tests 50%. Okay, here's one thing to remember, kind of the weighting that benefits you. So I'm keeping it open-ended, right? So we've had 2 tests so far, the one you just wrote, and then the first one. And so whatever works out best for you, right? If that's, 15% on test 1 and the rest on test 2, then so be it, right? But I'll just kind of play around with those and make sure that it works out. And then there's going to be just a final quiz for 10%. And what I want to do is I just want to quiz you guys on the last material, so it won't be cumulative anymore. So final quiz is not cumulative anymore. It's only on the last material, right? So kind of from today onward. Which I'll just say today onward. Hopefully you guys can hear me okay. I'm assuming that you'd let me know, but there was one person who couldn't hear me earlier, so she kind of didn't let me know, but looks like we're good. Okay, so so that final quiz, it will just be online, probably through Moodle, and it'll just, you know, test what we've done so far. Okay. I haven't marked your test 2 because I took the weekend off, if you can believe it. And so, but once test 2 is marked, once test number 2 is marked, you will get an email from Gradescope. So once you get that email, I'm pretty sure it'll say, you know, you've got some feedback, and so you can click on presumably a link. It'll get you to make a password. I'm just assuming here. And then you'll be able to log in and see the feedback that I've put on there. Right, so you'll be able to have your test and just kind of look at the feedback, look at the test, and then if you have any questions, then of course let me know. But that's how you're going to get your test 2 back. Okay. So I wonder, oh, do you guys want these to your personal emails? The ones that I've been sending emails to, or your My Okanagan emails?
Personal is fine, I guess.
Say that again. Was that Annabelle?
Yeah, personal is fine for me.
Personal is good?
Personal is good for me too.
Okay, let's use your personal emails then, just so you don't have to kind of ball back and forth between your My Okanagan and your personal. Is it mandatory to write the finals? Well, so this was just from side to me, but I guess you don't have to, but the final is worth 10% now, and it's just going to be that final quiz. So no, I guess if you don't want that 10% of your grade, you don't have to write it. But it might be nice. I don't know.
Okay.
Not your My Okanagan. Personal emails. Done. Okay, so that's what I'll use to set up your accounts and then that'll be good. Okay, so you'll get an email from Gradescope and once they're marked. Let's see if I missed anything else. Okay, good. Perfect. Okay. Any other? So one thing that we could do for this final quiz, because I do think that it was a lot easier to write the test on paper. What we could do is I could post a PDF of the quiz, and then we could and then you could submit your answers through Gradescope. So if that's something that you want to do, then we can kind of talk about that closer to the final. But the final quiz will be, I guess it'll have to be during final exam slot? I hadn't actually thought about that. There's so few of us, so maybe, well, okay, so as a rule, we're supposed to stick to our final exam slots. So I think that's when we'll use this designated time. We've got 3 hours. We definitely, like, you won't need 3 hours for this final quiz, but we'll just use the final exam slot. Okay, so let's do that just for simplicity's sake. Okay, what other housekeeping things do we have going on here? My iPad's running out of battery. Let me see if I can plug it in. Oh man, it's falling apart here. Whoa. Oh, might be tight. Yeah, maybe. Thanks. Thanks. Got a little stagehand here. Nice. All right, plugged in, ready to go. Well, I know what you guys were thinking. You're hoping that would mean that we were ending early. We still can't, but we can't because there's a lot of material. Okay. So any questions before we start finishing chapter 7? No. Awesome. Thanks, Annabelle. Oh, thanks, Elise. All right, then we will keep going. All right. So section 7.2. So 7.1, we just introduced interactions. I guess I'll start with a little review, but you were tested on it, so it's kind of probably pretty fresh. 7.1 was on interactions. Oops, interactions. And mostly we talked about, okay, interactions we can summarize as if there's a difference in the differences, which doesn't really make sense until you have a look at the table, right? And we saw we've got our factor, let's say B here, and our factor A. And then if we've got our differences here, and the differences here, right? If we had some differences and some differences here, we want to know if there's a difference in the differences, right? And so we talked about that, and visually, we can see these differences in the differences using an interaction plot. Where if we have parallel lines, means that there's no interaction. And that's kind of where we left off, right after we had to look at that table and looked at the differences, and then we looked at an interaction plot, and essentially we just left it at, okay, well, if you have parallel lines, then there's no interaction. And then of course, the alternative is that you don't have parallel lines, which means there is an interaction. So that's kind of where we ended off last day. So I'll do a little end of review there on that page. And then for 7.2, now we're just gonna deep dive into just the two-way factorial design, experiment, whatever you want to call it. So the two-way, remember two-way just means that you have two factors. And so same thing, two-way factorial. Again, just two factors, experiment. So I'll just clarify that here. Two factors. Okay. This section essentially just talks about experimental design, and we said, well, experimental design is its own field, right? And so we're not going to pretend to know everything about it, but there are some key things that we need to know. So experimental design, oops. There's 5 things that we need to keep in mind, right? And so when you're reading a study or anything like that, these are kind of 5 check-in points that you want to use just to see if they've used a good experimental design or maybe they haven't. But the first one, of course, is comparison, which, I mean, we shouldn't actually have to say, but we should study more than one condition. Study more than one condition, right? If you're interested in how fertilizer affects the height of the plant, you're not just going to give all your plants fertilizer and then see how much they grow, right? Right. You're going to study some sort of control as well. Study a control or more than one condition. Oops. Completely forgot a word here. More than one condition. I guess I said it later, so. Okay. So, and we know that from, the first stats course that you took, probably, and maybe even life before this. So that one is not that weird. Neither is the next one. So replication. Ideally, you want to measure more than 1 unit for each condition, right? So measure more than 1 unit for each condition. When I read this, what kind of came to my mind was, well, we said that when we introduced blocking, right, that we would only have 1 measurement per block. And then we expanded it to say, okay, well, now we can handle more than 1 measurement. But it's still possible to just have 1 measurement per block. But remember, each of the treatment, you had a measurement in each block, right? And so you would still have multiple measurements on each treatment, right? And so, of course, ideally you would have more, but the idea being that you don't just measure 1 thing for each treatment. So more than 1 measurement for each treatment, right? Not necessarily the blocks, even though you're going to anyways, but right, we're concerned about the treatments. Okay. So the third one is the blocking. So you want to be able to compare like with like, right? So you want to compare like things to other things to be able to figure out and drill down on the treatment effect, right? And so the blocking, you're going to arrange to compare like with like and isolate the effects of interest. And isolate the effects, I'll put that in brackets, the effects of interest. Right, and so you're blocking, right, just kind of remove some of that noise from the treatment. Right. So what we'll say here is block to remove some noise from the treatment effect. So if you're able to do some blocking, then you probably should. Like we said, your model's never going to be worse by blocking, right? It might not get any better, but it's never going to be worse from blocking. So you're never, blocking for no reason. The fourth point to keep in mind is we're just going to call it crossing. But again, it's one of those things that you would probably know anyways. Of course, you want to record data for all possible combinations of the levels, right? So if you've got a treatment and a blocking effect, then of course you want to look at all the different combinations, right? So you want to record data for all possible combinations of levels. Combinations of levels. Okay. That one kind of is self-explanatory, so I'm not going to clarify that one, but and I don't think any of you would go out and think that it's okay to not record data for all the possible combinations, so I'm good with that one. And then, of course, the last thing, let's not forget about the randomization of it all. Randomization. Right. We have to select randomly when I'll say when possible, right? Sometimes it won't be possible, but if you are setting up an experiment, right? So here we're talking about experimental design. So your experimental design should include randomization. So select randomly. Select randomly when possible. Okay. So those are kind of the 5 principles of experimental design. So whether you're reading a study or you're setting up your own experiment, right? These are all the basic checkpoints that you have to keep in mind. And what we said last day was in order to measure some sort of interaction, right, we have to have replication within each of the blocks. Right? And so in order to measure interaction, we need to replicate. Oops, that doesn't really read like replicate. Replicate. There. Okay. So what we're going to have is just a little bit of new terminology for the interaction, because what we're going to say, we're going to call the main effects are the 2 factors that we're actually concerned with, and then the interaction effect. And so we will have main effects and interaction effects. Where the main effects are just the factors that get crossed. The main effects are the factors that get crossed. And that's using the terminology that we used here in point number 4, right? Crossing is all the possible combinations. And so the main effects are the factors that get crossed. And then of course the interaction effect is the interaction between factor A and factor B. All right, so here, factor A and factor B, and the interaction effect is the interaction between factor A and factor B. So I'm pretty sure, and I haven't checked it recently, but I'm pretty sure in R, if you're doing an interaction, right, if you have, let's just call them A and B, right, before we were doing A multiplied by B, but because these are categorical variables, I am pretty sure, right, in R, okay, I need to check this. Right, I need to make sure that that's how it works, but so what you have is you would have your Y is A plus B plus, and then A colon B. I'm pretty sure. And that's your interaction effect. Pretty sure. Okay. So.
Oh, sorry, Emily, just a quick one.
Yeah.
So how does this one now differ? I think we also called it the A times B to B interaction, right?
Yeah, we can call it A times B if we want to. I was just thinking about like the actual R code to get that interaction in there. I think it might still work if you multiply them, but I don't know, for some reason this is what's in my mind as what it should be.
Okay. Because I just remembered from norms class.
Yeah.
So we were also discussing about interactions. So I think what the one that he introduced to us was A times B.
Yeah, so because that's what we used for numerical data. Did he use it for categorical data as well?
I don't think so.
Yeah, I think that's the difference. Because A and B are categorical.
Okay, well, we need to try it, I guess.
Exactly. Yeah. So here, I need to check this, Emily.
Yeah. Okay. Right.
How about that? So I'm pretty sure because interaction, and then I'll just clarify here, of two categorical variables, right? Because we did use A times B for the interaction in the regression case, right? So that's why I'm a little bit, I don't know, I'll have to check. But maybe I'll post some code or something, or I'll bring it next class. How about that? So, all right. But we can do the same thing. So the idea is still the same as in regression, right? These two things are interacting with each other. And we want to incorporate that into our model. Okay. So 7.3, if we're ready, we're going to be exploring two-way data. So this whole chapter is a little bit weird because the only new thing is the interaction, right? And so there's nothing crazy going on, but we just want to dive a little bit deeper into just two-way data in general. Is there an interaction? Should I be doing a transformation? That kind of thing. And so what we're going to be looking at is the center. So the center, oh, whoops. The center is going to tell us, you know, we get slopes between means to see if there's an interaction, to see if there is an interaction. So the centers, and then we're going to have the spreads. The spreads are going to tell us, so if they're roughly equal, then we don't need a transformation. But if the spreads are not roughly equal, we might explore a transformation. We might explore a transformation. So just for an example, right? Because sometimes it's hard to know, do I need an interaction? Do I need a transformation, right? And so just to have a look at some examples, the first plot, and I cram them on one page. I'll make them bigger for us here, but oh, maybe not, won't be room. Let me see here. And then I'll copy, I'll paste this here again. Wait. Crop. I just want to focus on, of course, just want to focus on the first one for now, just to talk about it. So I want it nice and big. And then we can go back and we can talk about the others. So these are all examples that are introduced in the textbook. But one way that we can show all this data, right, is we can use just the blocks. And so here, these are our blocks. And then I think it's whether they got a hormone or not. These are the treatments. And so these are birds. I can't actually remember what they are, but it doesn't matter. So each of them got a no treatment and each of them got the yes treatment, right? We split our males into two groups and then applied our treatments, same thing with the females. And so what we're looking for, right, is first thing we want to do is we want to look for the center. So the center of each of these, and there aren't that many points here. And so I'm just eyeballing here that my center might be somewhere around here. So these little points are my eyeball centers, right? So we don't need to get crazy here. And maybe I'll do a little bar through it just to show. So what I want to do is I want to look at the pattern between these centers. So here and here, oh, maybe I'll use a different color so it's not so same as the graph, right? So here and here, I've got a roughly equal. So here, this line is the slope between the mean. Slope between means. So what happens here is they're roughly equal. Here. And so here, for this data set, right, it looks like they're roughly equal, which means no interaction. So just by doing a dot plot of your data, right, and this is one of the ways you could do it. Another way that you could do it, and I'm going to use my fancy new pointer that they added recently, is we could overlap this guy, right, these dots, and put them over here and just use a different color. And I wonder if I put, did I put an example like that on here? I didn't. Okay, that's okay. Right, so this is just one way of doing it. Sometimes it's easier if we just kind of shift these over here and just kind of overlap them and use different colors. But in this case, it's pretty obvious to see that we've got the same slope-ish, right? So no interaction. Okay. If we do the same thing for these other graphs, and I'll make it bigger, just try to make it bigger so we can see. Da-da-da. Right. If I'm gonna kind of eyeball my centers here for this, for the pigs data, here's my center. I've only got 3 points here, right? And so there, here to here, whoo, I've got very different slopes, and so there must be an interaction. Same thing here for the rats data. They got different diets, and we measured the weight gain. If I just eyeball the center of these things, kind of roughly, maybe here, these slopes look very different from each other. And so it looks like there's an interaction. Okay. So you don't actually need an interaction plot, right? You can just use a dot plot of the data to see if there's an interaction. So now, let's see here.
One question, Emily.
Yes.
Can you go back to the rats?
Yep.
Yeah. So because this one is obvious, right? It's doing opposite slopes, right?
Yeah, totally.
But what if it follows the same slope, in the same trend, but different slopes, still interaction?
Do you mean if we had something maybe, so let's pretend that the means were here and here instead? And then you would have something like this?
Yes, something like that.
Then you would have less of an interaction, but I would probably say because this slope, this slope here, oh, let me use my fancy pointer instead. This slope here,
Yeah,
right, is less than this slope. So
yeah.
We're a little bit, lenient with that. And you could argue that you don't need to look at the interaction. What you would probably end up doing is just putting the interaction in there. And then if it's insignificant, then you can take it out and see what happens.
Oh, okay.
Right? And so if you're not sure, so unless it's obvious, like here, it's obvious there's no interaction
right.
going on,
Yes, right.
right? If you're ever doubting yourself, then I would say just throw an interaction term in there, see if it's significant. And then if it's not, then you could argue you could take it out and see what happens,
Okay.
right?
Right. Actually, it's related to the exam.
Say that again.
Related to the test, right? Yeah, we have
Oh yeah. But so for those things, as long as you're just arguing your case,
yeah.
right? Sometimes there is not necessarily a right or wrong answer. I just want to see you be able to argue it properly, right? And so you would hinge it on the slopes being the same or different. So in this case, so this made up case that we have with the orange slopes, you could argue, nope, these slopes are the same, so I don't have an interaction term. Great, moving on. Or you could say, well, because these are slightly different, I'm going to explore the interaction term.
Yeah.
And so I know you guys don't like that, but you've got options as long as you argue it.
No, what I was thinking is that because what you did in the exam is there were three lines, and all of them have different slopes.
Yeah.
But they were not touching each other, right?
Actually, I don't remember, and I'm not sure I have. Let me see here. Let's see if I have it here.
I think when you opened your note, there was a note that you opened earlier. I think it was there.
Oh, yeah, I've got it. Let's see here. I've got it. Yeah.
Figures, I think. Figures for March 23. Yeah, this one. Oh no, no, not that one, but something similar.
Oh yeah. Okay, I'm looking at the test one. And let's see, I don't have it quickly available here, so you'll have to put up with my drawing, but here we go.
Yeah.
So what we have is, it looks something like, the first one looks like this. Second one looks like, and I'll just use different colors, like this. Oops. Third one looks like
Yeah, something
that.
like, yeah, but they
Something like that.
each other.
I know I scooted these ones over. They should be kind of on top of each other, but I think you get the idea.
Yeah.
Right? So here, I mean, I would, and I have the advantage of being able to see the graph here, but the actual one, but I would argue that these lines are roughly parallel.
Really? You call it parallel?
Well, so here, so there's no interaction, right? Or if you said that because the lines are not parallel, we have an interaction, right? So as long as you argue it correctly, I'm going to be flexible, right? So so I would say that these lines are roughly parallel, because I think I'm more I don't know, loosey-goosey than you guys, but that's okay, right? So here, I think the problem is maybe this guy that you probably didn't like, I think. And I don't either, but you know, I'm more flexible than you guys on this stuff. So as long as you kind of argue whether they're parallel or not parallel, and then went for the correct conclusion, then that's all I wanted to see. Right? Does that make sense, Mano?
Well, for our study, yes. But what I'm thinking, if you're going to present same graph at work and present to a, let's say, a manager that doesn't really understand statistics. So if you say, oh, well, these lines are roughly parallel, what are you talking about?
Well, it's because you're focusing on each of the line segments.
Yeah, right.
Right? So for each of these line segments,
Okay. So
they're parallel.
what you mean now is that for as long as those lines do not intersect each other,
Yeah,
you can infer that they are roughly parallel and there's
yeah,
no interaction.
pretty well. Exactly.
Oh,
But again, if you're not sure, so if we are not sure, use an interaction term. And then remove it if it's insignificant. And remove it if it's insignificant.
yeah, okay. So I will go for the safer side, I guess.
Yeah, so so as long as you know how to argue it, that's fine. But in real life, right, if you're looking at something and you're like, oh, I don't actually know, then of course just kind of go ahead, use the interaction term. And I mean, you don't even have to remove it, right? And remove it, well, maybe not. You could just keep it in there and say that it's insignificant, right? Could keep in model as insignificant, just to show that you've covered your bases. So, because what we'll see, and I gave you some output in that figures document, right? And so here it only went to the F values, but an F of 47, I mean, is huge. So there is an interaction effect. And but if this F was small for the interaction, then you would just say the interaction term was insignificant, right? Okay. So, which ones were we looking at? Oh yeah, so now, so that's how we eyeball the centers and we just figure out what the slopes look like, and that's basically going to be our interaction plot. So we don't need an explicit interaction plot. So now if we go back and look at the spreads, right, we want them to be roughly equal, and so that's what we've been looking for in all our analyses so far. And so the spreads, let's say from here to here, and these are small data sets, right? And so we're going to be a little bit flexible, right? But it looks like the spread is small for the nose, right? And so here, this is the spread, okay? And it looks small for no, oops, for no treatment, or for no, and large for yes, right? Whatever the yes treatment is. So it looks like it's increasing as we move across the treatment. So depending on the treatment, right, it looks like it affects the spread. So what this tells me is that we might need a transformation. might need a transformation. And what we've talked about, right, is for, you know, Anova, it's usually going to be a log transformation. So in terms of okay, did I put this log SD on your? I don't think I did. We put it on the last one, but that's okay. Okay, so I'll just put my notes down here, but keep talking about these. So I guess we'll go back. So for the pigs data, right, if we look at the spreads, then here we've only got 3 data points for each of these. So again, we're going to be kind of flexible. There is some spread here that's less or some that's greater than here in the yeses. But the spread is relatively even between these 2 groups. And so because of the small sample size and because, you know, there's only one with different spread, I'm not too concerned about a transformation here. And so I would argue that we don't need a transformation for the pigs. So here, if we look at, you know, this spread, there's really only one. So for the pigs, the spread, there's only one that is different. Right, and that's the no. And so, and this is for the pigs data. So I would say no transformation needed. You could always, you know, try a transformation and see if it works. Remember, we plot the log of the standard deviations against the log of the means. And then if the slope is well, depending on what the slope is, then we'll be able to figure out what our transformation is. So you could still try it, but just at a glance here, I'm thinking there's no transformation that we need. Same thing here, right? For the rats data.
I have a question, Emily.
Oh, say that again.
I have a question regarding the transformation.
Okay.
So previously we used to take log of standard deviation and log of standard deviation.
Let me see if I can turn you up here. Oh. Okay, say that again.
So previously we just had one mean and one standard deviation of your treatment. Right now you have logs as well as treatments.
Yes.
So which one I'm gonna select to the transformation?
So you would do it on the response, right? And so you're still going to have your response, which is going to be all these ones on the y-axis. So unlike regression, where we could do transformations on the explanatory variables, we actually only transform the response for ANOVA. Yeah. Good question, because I forgot to mention that actually. Good. Yeah, so your response is the one that you would transform. Looking at these spreads, I'm just kind of using my fingers and seeing if there's any differences. There's kind of no differences in the spreads for the rats data. No differences in spread for rats. So no transformation. Oops. So no transformation. Oh, it doesn't want me touching it. And I'll just clarify of the response is needed. Good. Good, good, good. Okay. So just from dot plots, and if you've got a blocking term, then of course you incorporate that blocking term, and whether that's breaking it up like we've done here, you know, your blocks and then your treatments within those blocks, or if you kind of shift your blocks and use different, you know, symbols or colors or whatever, that doesn't really matter, right? Depending on what's easier to look at for you. Or if you're short on space, then you might want to merge them onto one plot. So same thing for the transformations. Transformations. If you're not sure, then do a plot of the log of the standard deviation against the log of the averages. So if you are not sure if you should use a transformation, right, make a plot of the log of the standard deviations for each of the treatment block crossings of the responses as your y against the log of the average is. Say that again. Oh, yeah. So this is the one that we've talked about before. So you use the same plot, but now you've got more points probably because you don't just have the treatment points, you have the block crossed with the treatment points. And then your power for the transformation is 1 minus the slope, right, which we've used before. So if the slope is 0, then we use log. And if the slope is 1, right, then, oh, now I bungled it one time and now I don't want to bungle it again, but I'm pretty sure. So if the slope is 0, then you can use logs. And I'll leave the other stuff open-ended until I can confirm with the textbook, but you've got it. I just can't remember off the top of my head. So if the slope is 0, then you're going to use logs. And so, all right, let's see here. So if we go back to your figures, okay, notice that one of the things that we could do, if you go to figure 7.9, copy, oops, to the notes. Okay. So here, these are 2 interaction plots. So the 2 interaction plots for the rat data, because what we're finding, right, is that, well, I could put, so for the rats data, right, I've got high protein as a block and low protein as a block. And then I think they got beef, cereal or corn or something, and then pork. Notice that beef and pork are behaving essentially the same way. And so, of course, we would probably just lump those into a meat category of some sort, but this is just to kind of lead us down that path. And so, but also to see more than two categories, right? And so we've got this blocking factor of the high protein, low protein, but then we've also got the different types of protein. So there's high protein beef and low protein beef. High protein, I want to say cereal, but I'm not, maybe it says on the graph here. Yeah. So here, right, we've got the different sources of the protein, and then there's high protein versions and low protein versions. So this is one of the ways that we could show this interaction plot, right? We could show the means of, and notice that pork and beef are basically overlapping here. So it looks like there's only one line, or two lines, but there's actually three. So here, right, it looks like beef and pork behave the exact same way. We could probably just lump them into one group. And then, so it looks like in terms of weight gain, if weight gain is what we want, then to me, it looks like, okay, if you're feeding a high protein meat, then your rat is going to gain a lot more weight than a high protein cereal, right? Whereas if you're feeding low protein everything, then the cereal looks like it's actually going to make it gain more weight than the meat, right? A low protein meat doesn't perform as well as a low protein cereal. So cereal seems to not really change whether it's high protein or low protein, whereas the meat, the weight gain really depends on whether it's high protein or low protein. So that's kind of interesting. We see that same information in the next graph. And so this is another way that we could do it, right? Is if we have our blocks are on the x-axis and then our groupings are the treatments. Or if we've got our groupings, the treatments here are on the x-axis, and then we've got our blocks making up our lines. That's another way that we could do it. Both of these graphs tell us the same thing. They give us the same information. In this case, they're equally useful, right? I would say probably for me personally, the first graph is a little bit easier to read and understand than the second one, right? If we're talking about beef, then we're getting that same information that the low protein beef gives us less mean weight gain than the high protein beef, right? Same thing for the cereal, except they come together here in this kind of, I don't know, pinch, right? A bow tie type pinch, because cereal is, the mean weight gain is going to be the same-ish, regardless of if you're high or low protein. And then same thing for the pork. Low protein pork gives you a low mean weight gain, and even lower compared to the cereal. But then of course you get a high mean weight gain if you have high protein pork, right? And so one thing to keep in mind is that these graphs, or these plots, both show the same information. Yeah. And in this case, both are going to be useful. Some cases, you know, there's going to be one that's easier to read, so you only need to do one, but I just wanted to show you that, you know, there's two okay ways to do this, right? There's no kind of logic behind it. So in this case, both are useful. Okay. And in general, there is no way to determine, there is no way to, I'll say predetermine, which plot will be more useful. So that's tricky, right? So you would just make both, see which one is easier to talk about, and then use that one, right? Especially if you're making a presentation or something like that. I would probably have an easier time, but maybe that's just because of how I present. I would have an easier time explaining this graph than this graph, right? And so that's why I would pick the first one. But if you have an easier time explaining this one, then you would use that one, right? So there's no reason why you should use one over the other. One thing to keep in mind is that sometimes if you have a quantitative factor, right, then that would be probably the best one to put on your x-axis, only because then you'll be able to sense some sort of trends as you move along, right? And so here in the next figure that I've given you, there's this dinosaur data. So what they've done is they're trying to figure out, I feel like they were trying to figure out what killed the dinosaurs. It's a pretty fun study. So they've gone ahead and they've measured the mean measure of iridium in each of the soil samples. And so like here, they went down to different depths. And of course, these are quantitative, well, they're numbers, right, that have been converted into categories. So anything less than 345 is in the 345 column. Anything between 345 and 346 is in the 346 grouping, right? And then between 346 and 347 is in the 347 grouping. And so it just kind of, we've made categorical variables from the numerical variables. So here, maybe I'll highlight these and say that these are numerical variable turned into categories. Here, I would say, and just as a rule, we're going to use the first graph instead of the second graph. Right? The second graph is just kind of way too busy, way too much going on here. It doesn't really tell us anything about the depth, whereas here we're getting this kind of clear overall pattern. And maybe even this one is good to be able to look at. Would I say there's an interaction here? Probably not, but because of this little region here, I would want to look at it a little bit closer. So I would probably build my model with an interaction term to see what was going on, and then kind of go from there, especially because you've got that same crossing over here. But remember, these two graphs tell you the exact same thing. Right? And so what I'll say here is that if you have a quantitative variable, quantitative, man, that's hard, / numerical, no wonder I use numerical, / numerical variable, or factor, I should say, use it on your x-axis to see if there are any patterns. To see if there are any patterns. So that's what you'll want to do. Okay. 147. I am struggle city with how much time I have left. I don't think I have that much time left. do I? Why is that someone?
You have 3 minutes.
3 minutes. Oh man, I'm all confused because I'm 3 hours ahead of you guys. So, okay, 3 minutes. Make them last. Well, I was just about to start a new section. I guess we can do it next day. What do you guys think about that? I was about to do.
Well, if you're going to consume the lab, then you still have time.
I know. Do you guys have time to use the lab time?
Guys?
Hello?
Oh?
Uh-oh.
Yeah.
Yes.
Yeah. Okay.
Yeah. Do that.
Do you guys want to take a 10-minute break and then we'll start this back up again?
Yeah, that'll be good.
Okay.
Yeah, let's do that. So I'll just pause this. Cool, thanks, Lise. And then I'll use that lab time. How about? I know, sorry guys. Close this. And also because my battery is dying. It's plugged in, but it's not helping. All right, I'm gonna pause this. Okay, we are back. I'm not on mute. I would do something like that. And looks like we're all a go. Okay. Where's my next page break? Okay, fine. I'll just start here. So section 7.4 is on the actual fitting a two-way ANOVA or a two-way balanced ANOVA model. Okay. And so, oh, I guess I could have used that time to figure out how to do it in R, but if we just look at the output for now, I just want to talk about it and then can do that next day. So here, paste that in here. Yeah. If we've got this ANOVA model, and if we're looking at the pigs data, then we've got this interaction term here. Right? And if we go back to not really knowing or caring about what the pigs study was, that's for the rats or the pigs here. We said that there probably was an interaction just because this slope went this way and then this slope went this way. There's obviously not the same slopes here, and so so we said, okay, I'm going to include an interaction term, and of course, once we have a look at that output here, the interaction term is significant, right? And so what we said earlier was we don't get the p-values quite yet. We will, of course, if you run it in R, but a large F value means you're going to get a small p-value anyways. So I just want to talk about what these Fs are, because we're only used to seeing one F, but each of these Fs are going to be from the mean squared of each of those treatments or the factors, and then divided by the mean squared error, so the residual mean squared. Okay, so so the 60, for example, this is going to be 2187 divided by 3625. Right, the 5 is going to be 192.00 divided by 3625. And then for the interaction, we've got 1728 divided by 3625. And so that's just where those come from. And so how we interpret these. So to interpret the F statistics, for the first one, if we look at the B12 factor, we would say, okay, the average variation in the means, so that's the mean squared of B12. So the average variation of B12, which is communicated by the mean squared of the B12. So for the main effect, so remember we call B12 and the antibiotics, those are main effects, and then we've got this interaction effect, right? And so the average variation for B12 is more than or roughly 6 times as large as the average variation for the residuals, right? Which is the average variation from pig to pig in this case, because we're talking about pigs. So what we say is that the average variation, which is the mean squared of B12, oops, B12, for the main effect B12 is more than 60 times as large as the average variation, oops, as the average variation from pig to pig, which is the mean squared error. Right, and so what I want to highlight here is the variation from pig to pig. This is the, or I guess I should include the variation. This is the residual variation, right? The variation from pig to pig is everything that's not captured by the blocking factor or by the treatment factor or even the interaction term between those two things, right? And so that's the residual variation. And 5%. Okay, we're just gonna go until this thing dies, I guess. I'll have to call it before then. It's plugged in, I don't know what else to do. Good. So that's where that 60 comes from, and that's how we interpret it, right? And so if we do the same thing for the next one, right, then the average variation in that's due to the antibiotics, right, is just about a little over 5 times as much as the residual variation, right, 36.25. So our next one, right, the average variation due to antibiotics is much smaller, a little more than 5 times as large as the average residual variation. And then same idea, right? The average variation due to the interaction is about 48, so 47.669, so roughly 48 times the residual variation. And so that's huge. And so the average variation due to interaction is large. So it's almost 48 times the residual variation. The residual variation. So even without p-values, we understand that these large f values mean that these things are significant, right? These factors are significant, whether that's the main effects or the interaction effects, depending on which f we're talking about, right? In this case, I would guess that even the antibiotics effect is going to be significant at 5, right? Because remember, an F statistic of 1 is going to be insignificant, right? And then it's just going to increase from there. So once we hit 5, I'd say that's relatively large. It depends on our degrees of freedom, of course, but my guess is that that would be significant as well. And because the interaction term is in there and it's significant, we might not have a choice. I think we would just keep it in there because it doesn't really make sense to have an interaction without it. So if the interaction is significant, then of course we would just keep both our main effects and our interaction effect. In fact, I'll put that on here, right? These two are our main effects. And this is our interaction effect, of course. Okay. So that's basically the only new thing. We don't get p-values quite yet because we haven't checked any assumptions. And so in the next section, we're going to be assessing the fit. And so that's when we're going to look at the diagnostic plots. We've seen all these before, right? But we're just going to talk about them again. So let's go into section 7.5. Assessing the fit, or assessing fit. Oops. And I've put some diagnostic plots on your figures here. This is the one I want, this last one. Copy. Paste. So just to talk about these a little bit, right? And let me just flip forward to see. Okay, good. See where we're headed. How much I have to do before?
It's your charging is 3%. It's good to end before it dies, so that we know we have ended, I guess.
Wait, say that again.
Your charging is 3%.
I
It used to be
know.
5, and it's going to die, I guess.
I think so. I'm worried. So
Yeah.
I think once we hit 1%, then we'll have to call it.
Okay.
Yeah, because I don't know how to make it charge any faster.
Okay.
Are there any tricks out there?
Nope.
No.
Buy
We're
new
just
iPhone.
you can buy a new iPad. Yeah, there's an option. Yeah, I don't know. Yeah, it's all charged or plugged in. I don't know. I just don't know. But anyways, once we hit 1%, I'll keep an eye on it. Then I'll have to save the video because I don't want the video to be lost. I don't think it would be, but anyways. So until then, we'll keep going through 7.5. So all these diagnostic plots we've seen before, right? We plot our residuals against our fitted values. We're looking for random even scatter around 0, right? Here, we might say that we've got this kind of wedge thing going on. It depends on how things look. And if we move over to the normal quantile plot, things look nice and normal around here, but there is this kind of huge deviation in the tails. And so this to me indicates that we'll probably need some sort of transformation, and that transformation would probably deal with something with what's going on over here as well. And so in this case, let's make a couple of notes here. Part A. In our residuals versus fitted plot, right, what are we going to do? We're going to check for a curved pattern. I see none in this case. Right. Check for a wedged pattern. Right. A wedged pattern, and even a curved pattern too, but definitely a wedged pattern. A wedged pattern, and by that I mean something that kind of looks like this. Wait, I guess that still works, but just kind of right. Here's this kind of wedged pattern. Wait, like this. So a wedged pattern suggests transforming down. And what I mean by that, suggests transforming down. And so transforming down is to powers less than 1. Right, and so if you want a square root, then the power is 1/2, of course. Oh, well, I should write power. Power is 1/2. If you take the log, then your power is 0. Right, and this is in the standard deviation against your, the logs of the standard deviations against the logs of your means. And then if you want the reciprocal, then your powers should be -1, right? Notice that all these powers are less than 1. So this is what transforming down means. All of those are good options, but of course, our star player is the log. Right? Usually that's pretty good. And these powers use the log of the standard deviation against the log of the x bars to determine the power, right, for the slope. So the power is still 1 minus the slope. So same one as before. So that's the first plot, things you're looking for, things you're looking out for. In the second one, we talked about the QQ plot. So the QQ plot B is the QQ plot on, I'll say, some indication of non-normality in the tails. This tells me that I should also probably transform down. So this is another kind of check-in point that you can use. And so here, suggest transforming down. Right, and we talked about that before. Transforming down. So Hey, it jumped up to 3%. Woohoo. What was that too? So the third plot is the Tukey plot, right, where we plot our residuals against the comparisons. And I forget how to calculate those comparisons, but that's okay. We've got it in our notes somewhere. And so the Tukey plot, or the Tukey additivity plot, right, says, well, it asks and answers two questions. So is there a scale for which the main effects will be additive, right, with no interaction? And so if all these points kind of have a linear relationship, right, or a roughly linear relationship, then the answer is yes, right? That means that we can probably model this thing without an interaction term, because there is this sort of additive relationship between the two factors. And so, and if they're not on the line, so let's say you've got this non-linear relationship, then you probably can't use an additive model, and you have to find something else. And then the second question is, okay, well, if I need a transformation on these guys, what transformation would I need? Oh, and all of a sudden, dang it, I'm at 1%. Okay, let's see if I can pull this off. What if I let my screen sleep for a little bit? Do you think that's better? I don't know, man. Okay. What I'm gonna do is I'm gonna pause the recording for 5 minutes, let it charge, and then I'll come back. Sorry, guys. It might die. It's at 2%. Oh, I know. Crazy, right? Okay. So let's see what we can do here. Start the recording. I'm not on mute. Okay. So what we've got, right, for our third plot is the Tukey additivity plot. And so it answers two questions. The first one is there a scale for which main effects will be additive with no interaction? So is there a scale for which main effects will be additive with no interaction? Right, and so the answer is yes, if points are near a line. If the points are near a line, and no otherwise. And the second question it asks is, well, what's the transformations? So if there is such a scale, then what does the transformation need to be in order to make that happen, if there is any? So what transformation do we need? So again, just kind of a guide to transformation. Well, the transformation, the power of the transformation is just going to be 1 minus the slope again. Right, so the usual. The fourth plot is that plot, and again, right, same thing, the log of the standard deviation over the or against the log of the cell means. So again, we're looking at the slope between these two things to determine what our transformation should be. And then, so here, kind of more eloquently, D is the log of the standard deviation against the log of, I'll just call them the X bars. And it also answers two questions. So it answers two questions. The first one, and it's slightly different, right? So here in the Tukey additivity plot, we want to know if there's a scale for which the main effects will be additive with no interaction. Now what we're asking is there a scale? Is there a scale for which the standard deviations will be roughly equal? For which the standard deviations will be roughly equal. Right, and so here, the answer to that is yes. Again, if the points are near a line, if the points are near a line, and of course the answer is no otherwise. So if that's not the case, then no. The second question is, of course, well, what transformation would we need to make that happen? What transformation? And again, same thing, you know, someone figured out, okay, well, if I can figure out the power by using 1 minus the slope, let's do that for all of these things. So here, what's important is that in the Tukey additivity plot, right, we want to know if the main effects will be additive with no interaction, whereas in the log of the standard deviation versus the log of the means, right, we want to know if the standard deviations will be roughly equal. So those are answering two different questions, and you might arrive at different transformations. So from C and D, you might arrive at different transformations. But there's no harm in running multiple transformations. Okay, so in that case, there is no harm in running multiple transformations.
But you, for doing transformations, you should only apply one, right?
Yeah, so you only stick to one in the end, but you can run both. Like you can do, let's say, a square root transformation and a log transformation, and look at the output side by side, and then just kind of see which one looks better, right? We don't have things like the R squared values or anything like that, so it doesn't, you know, generally it doesn't matter, and that's why we just tend to use the log. But maybe, you know, maybe it makes more sense to use a square root, but typically we just run with the log and use the log.
Yeah.
So, yeah. Okay, so one thing though, just as before, right? So if you transform data, right, then you might want to back transform it to be able to talk about, you know, estimates and confidence intervals and that kind of thing. So if you transform data, it is often helpful to back transform estimates and intervals. Estimates and intervals to original units. Just for interpreting your data. Okay. So I think that's all I'm gonna cover today. I know, sorry about the battery. I went into today with a full battery, so I'm really sorry, but I guess I'll just have to keep it charged or charging the whole time on Wednesday. So anyways, now I know, but that's okay. 7.6 we'll cover next day. It's just, I'm just gonna talk about the theoretical model, which is really just adding that interaction term. But then we'll be done with chapter 7, then we can move on to chapter 8. All right. So, little choppy, but I think we'll do just fine with this online delivery thing. Okay. All right. Let's see.
We're still here, don't worry.
Yeah, I know. Any questions though before we go? I'll let you unmute yourself if you do. Nope.
And so far, I think no questions.
No questions. Awesome. All right. Well, thanks guys for coming. And I guess I'll well, not really see you guys, but I'll hear from you guys and you'll hear from me on Wednesday. All right. Let's end this recording here. See you later, guys.
Thanks,
See
Emily.
you. Thank you.
See ya.
Bye-bye.
Bye.